Here's the walkthrough for your exam. Question number 1 was to describe 3 purposes of the operating system. Now, there are 8 different parts that we've looked at. First of all, managing the processor. It manages all our interrupts, the ISR, and decides which process to complete next. Remember, usually that is given a priority to all different tasks. Number 2 is memory management, allocating memory, including paging and segmentation and virtual memory. Remember, in these examples, I'm expecting you to give information about what that is actually doing and its purposes. The operating system also manages external device drivers. Remember, a device driver is the bridge between the user and the operating system. This allows us to use any hardware on any system and any software. That means that the device driver translates operations and instructions into those which are understood by a specific device. It also provides a platform for application software and utility program. This means that we can run those applications, and remember, they have a similar look and feel. It provides us with networking, so that we can communicate through protocols to other devices not on our network and elsewhere. One of the biggest things that it does for us is manage security. So it services and denies requests to access our resources as well, and then provides a user interface for us so that we can interact through an interface provided, such as a GUI, a WIMP, or a command line. Question number 2, what is meant by paging? So remember that we divide memory up into fixed pages, which are 4 kilobytes each. And when we have memory and we don't have enough contiguous memory, we're going to use something called a page table, which maps where we're storing the link between the physical memory addresses and the logical space between each section of memory. This is because, remember, we can't store all of that process in one block. So we split it up and split it between memory. To use paging, remember, we're going to be able to have enough space in memory to actually store the program that we're trying to open. Otherwise, we'd have to shift a program to virtual memory first before we can load a program into our memory. And then we might use paging or segmentation. Question number 3. I was expecting you to identify that this data is stored in logical divisions rather than set sizes as 4 kilobytes. This means very much it depends on the programming structure. So if you think of a program, it might store a loop together, or it might store a function in one place. With both of these, remember, we can load only part of a program into memory, but a disadvantage of segmentation is that we could have a large data structure, such as a massive for loop, and we might not have space for that particular logical structure in memory. So remember, when memory is full, we can think about question 4 now, we use something called virtual memory. This is where we use our secondary storage, like our hard disk drive, as an extension to our memory. We quite often allocate a small amount of memory in our storage, in our secondary storage, which can be used for virtual memory. If a large number of jobs are loaded and the computer actually has insufficient space, then we're going to actually have to swap those pages in and out, called disk hashing. We're swapping those pages in and out of RAM, so we swap the one that's been least frequently used, or the one that we don't need at the moment, into RAM, into the hard drive, and we swap the program that we do want to use into RAM. So question number 5, what is an interrupt? So an interrupt is a signal sent to the processor saying that something needs attention. That might be a device, such as an input or output request. It might be the power button has been pressed on the computer. And remember, there are different types of interrupts as well. Each one is given a priority, which is usually higher than the other processes that are currently running. We'd want to service an interrupt first, and we have an ISR, on interrupt service routine, and the question 6 was, what is an ISR? This is a service routine which deals with the interrupt. So once we have an interrupt, it will depend on the actual routine that's going to be called to service it. Remember, the current processes are moved from memory into a stack data structure in memory, and the ISR will decide on the priority of the interrupts, and if there's more than one interrupt, which one is going to run first. So then this leads us on to question 7. What actually happens in an interrupt? So we've said some of this already. If the interrupt is lower or equal priority to the current process, then the current process will continue. More often than not, though, an interrupt has a higher priority. Otherwise, interrupts would never work. So the CPU would finish its current FDE cycle and copy the contents of the registers into the stack in memory. This is so it can carry on with this instruction, this processing, once our interrupt has completed. Then the ISR decides what's going to happen. So our interrupt service routine is loaded into the program counter, and once that is complete, the interrupt has been completed, we can remove everything back from the stack back into the register. And that's great, but we need to think about scheduling. So a scheduler, in question 8, and what's the purpose of it? The purpose is to maximise throughput, to try and get as much processing done as possible. You could also have put to be fair to all users on a multi-system, to provide acceptable response times to all users, to ensure hardware resources are kept as busy as possible. There's no point waiting for a user input. We could be using that processing time for a different job. This means that we can process as many jobs as possible in the least possible amount of time. That's what we're aiming for with using a scheduler. We maximise the number of interactive users with response times, so making sure those response times are fast and helping us to ensure an efficient use of resources and processor time. So there are lots of different types of schedulers, and question 9 asked you what's meant by a round robin. Well, basically the first one in is the first one out. So the first one that comes in, we complete before that one finishes. However, in a round robin, each process is given so much time, what we call a time slice. So if that process doesn't complete its time slice, it then goes to the back of the queue, and the next process takes over in the CPU. And that process keeps going until the jobs have finished. This actually gives us a reasonable time to all different processes, and it allows the user, it actually makes the user think that more processes are running, gives us that multitasking appearance. The second one was shortest job first. Well, this, we have to estimate the running time of each process, and obviously this is quite complicated, remember. And it completes the job with the shortest estimated running time first. If there is some form of application, though, that might have a quite large process that it needs completing, this might never be completed. However, we get rid of a lot of the smaller jobs quite quickly. Then we had a multi-level feedback queue. Now remember, we have every job is given a priority, and we have lots of different queues. Remember, our model that we looked at had 3 different queues, high, medium and low, with a ready queue as well. This means that we can give each process a priority, a category. We've got several of these different job queues running, and we can give preference to a certain type of job. Then we looked at the different types of operating systems. So question 12, explain a multitasking operating system. Now, a multitasking operating system gives us the appearance that more than one app is running, like using a scheduler, like me and you use every day in school and at home. We're using a multitasking operating system. This gives us the opinion that more than one process is happening at the same time, and usually each process is given a time slice, a bit like a round robin on a PC or a laptop. Number 13, what is meant by an embedded system? Now, we've done an awful lot of information about embedded systems, and you should be developing more of a complex understanding of these now. So they run off dedicated hardware. Think of a speed camera which is on a road. You could only use that hardware, the camera, in that format for a speed camera. They have a specific task. Now I'm adding to the answer now because you should hopefully also know they have a basic user interface. This might be a command line interface. Think of a microwave that only has a couple of buttons and it's very, very basic. And quite often it's a very basic operating system as well. They are usually Harvard architecture, as that might mean that your data and your instructions are separate. And we're probably looking at a RISC processor as well. So then question 14, describe real-time processing. Processes that are executed within a certain time frame. So you can think of critical systems such as driverless cars, or quite often if you're looking at missile launchers and those kind of things, or rocket launchers. The system has to react straight away to what is happening. They have to be what's called safety critical. We can plan for this by building in some redundancy. By building redundancy, we're never going to use up all the resources, and this allows our system to respond to what is going on. We need almost instant responses. Question 15, what does BIOS stand for? It was Basic Input Output System. Question 16 is, what is a BIOS? Well, we know that when we turn on a computer, the CPU doesn't know anything that's going on at all. Remember, it is volatile, so it's lost any data inside of it, as has RAM. Now, our initial startup sequence is held in ROM. This could actually be flash memory, so it retains its data when the computer is turned off, so it's non-volatile. We have a loader which loads the key parts of the operating system from memory into the CPU, obviously into RAM, and then the CPU starts processing those instructions. And our bootloader then allows us to load the operating system, which, remember, the operating system then takes over excuse me, the management of the operating system and the computer. We also have a post. This happens right near the start of this BIOS sequence. This checks that the hardware is installed properly. So do we have our memory there, our RAM? Is our hard disk there and working? Is our processor there and working as well? And checks that that system is suitable. Question 17, what is a device driver? We've touched on this quite quickly already. It's a small piece of software which acts as an interface between the device and the operating system. In the olden days, you'd plug a device into the computer and you'd have to load the device driver to make sure it would work. Nowadays, we have plug-and-play devices. This enables the operating system to actually access the hardware. It takes all the pain from the operating system in having to actually communicate directly with the hardware. So that means it can work on more than one system. The next part, what's a virtual machine? So a virtual machine, remember, is a program which almost provides the same functionality as the machine as if it was running on its native hardware. Pretend you've got a brand new games console, a PS5, and you want to run an old game which would only work on, let's say, a PS2 or a PS3. Well, you can get some emulators or a virtual machine, which allows us to run that game but on different hardware. So it emulates it on a different type of hardware. And the final question, where could we use virtual machines? Well, very regularly, we said it already, in games. Quite often in operating systems, we have virtual servers as well. We would test new software in a virtual machine. So if you remember, we would test virus protection. So we don't want to damage the machine we're running it on, so we want to check that, and that means we can restart that as well. And also intermediate code. So remember, we've talked about Java and how Java uses intermediate code so that when you have a program on your computer, it runs that code on a virtual machine. It's like having a different machine on yours, so that program will run on your machine without having to download a massive program.